Okay. All right. So today we're graphing parabolas, which come from a quadratic equation, specifically from factored form. And I hope that we can tie all three forms that we talked about together after we do this example. This will also relate to when we graphed polynomials from factored form. Sometimes you were given a polynomial in standard form, and then we put it into factored form to do what we needed to do. So before I started recording, we did a little recalling where we used our little mnemonic device here. Stinky Yetis enjoy ballet and fuzzy zombies play mind games. Stinky stood for standard form. Standard form looks something like the following. I'm going to do 4 examples of standard form. Maybe it looks like this, ax plus b. That would be linear in standard form, which you usually see mx plus b. Maybe it looks like this, ax squared plus bx plus c. That would be a quadratic trinomial, linear binomial. Ax to the third plus bx to the second plus cx plus d. That's a cubic polynomial of 4 terms. Maybe something like a x to the 4 plus bx to the third plus c x to the second plus d x plus e. And this can carry on for ever and ever. Even we could have just had a constant, a. So we would end up taking these things that were in standard form, and the easiest thing to find were the y-intercepts. What are the y-intercepts in all of these? If we had y equals, these are all graphable on the xy plane. We have x and y as our variables. A, B, C, D, all the way to E would be our constants. What are the y-intercepts when you look at something in standard form? Can anyone share with the class? Go ahead, you want to go for it, Paige?
I'm going to do the constant term, so B, C, D, E, and A.
C, D, E. Okay, the ones at the end though, because there's C's, D's, and E's everywhere, right? Well, there's only one E, but so A is the y-intercept. I know it's always awkward in the ones that are very simple because you're like, they feel a little naked. Like, I don't want to commit to giving this guy this big job. There's only 2 of them in the equation doing all the work, but y-intercept, 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 and so on. So in y equals mx plus b, we always said that this was the y-intercept. It's no different in any other equation. So my y-intercept, Yetis, is always that constant. Really, I guess the sign, if it's plus, it would be a positive y-intercept. If it's minus, you have a negative y-intercept, and so on. Then EB was end behavior. End behavior was a struggle for some people. It's a little awkward to remember. So really you had to know 2 things to be okay with end behavior. What did the end behavior depend on? What did end behavior depend on? Does anybody remember? I'm going to flip to a clean page before we really get into this example. This is another thing we're going to try to remember right now. So end behavior. Now this whole concept is super important all the way up until calculus, if you're going to take up to calculus. I think, did Ariel have her hand up or you backed away? Or are you still in? Oh, there you are. Ariel, what do you remember about end behavior? Okay, good. So really we looked at the leading term. Now what the heckers is a leading term? Well, here, the leading term, I guess I'll circle the leading term in blue for us. The leading term is the entire expression with the biggest power in the equation. So ax squared, ax cubed, x to the 4th, and so on. So what I just circled there was the leading term. So I'm going to encircle enjoy ballet with that color. I'm going to circle end behavior in that color. And I'm going to go now to our little side notes over here. End behavior. And we're going to look at our leading term. Now the leading term, Ariel said it didn't matter if it was positive or negative, and that's absolutely correct. So we would have a x to a power, okay? I'm going to use the word degree. Degree is the name of the power when a polynomial is in standard form. So let's write that down because that is one spot people mess up. Degree, the biggest power when a polynomial, this matters, is in standard form. It's the biggest power. Okay, so A out front could be positive or the A out front could be negative. So I'm going to make a little chart. It matters, we said, if it is positive, Ariel reminded us. So that obviously means positive does one thing and negative does another thing. That's one thing the end behavior depends on. And who remembers the other thing? How about, go ahead, Liana? If the degree was what? Right. Everyone does that. I do the same thing sometimes when I'm talking. I feel like those words jumble up. So is the degree even or odd? So I'm doing these little curly brackets so I could say what I'm referring to so you don't get mixed up. Degree, even or odd, and then leading. I guess I could be specific in the sense that I'm going to say leading coefficient. So the leading coefficient, is it positive or negative? And the degree, is it even or odd? Now, what do we know about the end behavior in any of these cases? Maybe we start here. It's usually easiest to start with the positive or negative. If your leading coefficient is positive, what did that say about the end behavior? Remember, the ends we're talking about are the left and the right of your graph. So the left and the right of your graph could be pointing upwards. They could be pointing downwards, or you could have one of each. One side, which way do I want to go here? One side pointing up and one side pointing down, or the reverse. So what does it tell us? We're going to start here. If the leading coefficient is positive, overall, your graph is going to be going which way? Who remembers? Go ahead, Justin.
It'll be going up.
Yes. If your leading coefficient is positive overall, at the end, your graph at the right end, at the finish, will be going up, whether it's even or odd. Okay, that being said, what other conclusion can we make? What other conclusion can we make? Justin, you want to tie it together for us?
Yeah, so negative would be down.
Yes. Negative, if it's negative, it'll be pointing down. This is my only like legit green highlighter, so I'm really holding on to it, so it's pretty dry. Okay. All right, now who's going to help us out? What happens for even graphs and what happens for odd graphs? What happens for an even graph and what happens for an odd graph? Evens and odds. Let me grab two highlighters. Give me one situation, Isa, or maybe you'll tie it all together. We'll see.
For even, it's the same way.
Good. So for even, if the degree is even, it's the same on both sides. So since it's up on the right, then it's also up on the left. And if it's down on the right, then it's the down on the left. So even it's the same on both sides. That being said, we want to figure out now the odd. So if it's odd, what can we say about the beginning of the graph, the other end? Go ahead, Marta. I'm sorry, say it again.
The beginning is going downwards.
For this one, it would be going downwards because this side's going upwards. But what about this one? The one under it. Would that be going down as well?
Yeah.
Well, this one's already down, down.
That one would be going up, down.
Yes. So what was the way we remembered for odd? So the even, we said the same thing happens on both ends. For the odd, if it's not the same thing happening on both ends, you could say the blank is happening. Good, Jabari. Yeah, opposite. So the opposite thing would be happening on both ends. All right. So we just make a little mental note of this, save this in our memory so we don't forget it. I actually just spoke to someone that I had in Algebra 2 last year the other day through email. And I asked her how class was going because she has pre-calc this year. And she said, actually, all the graphing stuff we did last year helps me out a lot in pre-calc. She's like, so it's really, really helpful. So this is gold, okay? All right, so I'll drill it into you, okay? End behavior, then fuzzy is factored form. So factored form will look something like this. We'll talk more about factored form as we go. Zombies, we wrote the word zeros. We went over the spelling over here, comparison. What are zeros? What the heck is a zero? Like just the number? We just write zeros on our paper, call it a day? Zeros, zeros. So I have three hands up maybe, but I think they're up from before as well, but maybe they're still up. But give you guys another minute. What are zeros? They're the real heroes of our graphing. They help us out a lot. Zeros. You want to tell me what zeros are, Paige? What are zeros?
Zero would be x.
Exactly. 0 are our x-intercepts. We're going to plot those points. Multiplicity. We're going to check on the multiplicity. What the heck is a multiplicity? I said it's sort of like degree. What's a multiplicity? Multiplicity. Maybe you want to tell me what the multiplicity is of these factors here. Maybe you want to make up your own example. Multiplicity. Go ahead, Liana. What do you know about multiplicity?
All the degrees.
Well, okay, the degree is all the multiplicities added up.
Oh, okay. So they're like the degree of each term.
Yeah, so each one has their own multiplicity. And if we expand everything, that will be the degree. So here again, the degree, I'm going to write so I'm trying to take my time so you guys could add these details to your notes too. Degree, where you would see over here, and now I know I used pink on like the other page, but I'm going to use it again here. If you remember, my initials are DT, so first name, last name, and I said D is what we do to classify our polynomials first, and then T is what we do to classify it second, like first name, last name. So degree would be like linear, quadratic, cubic, quartic, constant, because we don't have a degree there, right? Well, the degree is 0. And then number of terms was how we classified it second. So monomial, binomial, trinomial, polynomial, 4 terms, and so on. So the degree is when it's in expanded form. And the multiplicity is when it's in factored form. Okay. So each factor has a multiplicity. Okay. Each factor has a multiplicity. So what's the multiplicity of each of these? What's the multiplicity of each of these? Kennedy, go ahead. What's the multiplicity of each of them?
Would it just be 1?
Exactly. When there's nothing there, it's actually an invisible 1, not a 0. And the 3 multiplicities that we talked about were 1, 2, and 3. We talked about 1, 2, and 3. I guess I could put it on this page here. Multiplicity. 1, 2, and 3. We had a word for each one, and then I could draw a little picture of what happens at the zeros. So this tells us, showing a little arrow, what happens at each 0. And we just said that a 0 is an x-intercept. Does anybody remember the words that went with each of these? Like when this was 1, we said it was blank behavior. So we had an L word, a Q word, and a C word. So let me hear from you. Let me hear you try. I know Marta's hand is still up from before. I'm not sure if it was on purpose or accident. I'm gonna make sure. I see Liana and Kennedy, but it'd be nice to hear from some of you guys that are being a little quiet. I know Adriana had her hand up before. I didn't get to call on her. Maybe Dylan or Ella, Hashara. Who else? Manuel, you there? Melvin, Natalie. This is old stuff. Sean and Soul. So I'm not even calling on you guys for a new topic at this moment. Tahani, you know, I'd like to hear from you guys on something a little refresher. Take advantage. What's a word? The L word, Q word, and C word. Which word can you give me? Go ahead. Adriana, give me one of them. Manuel, your name's not Adriana, but yes.
Sorry.
All right, Adriana, give me another one. Quadratic. And give me another one for, say, this one over here. Ariel? Oh, Dylan. Cubic. I was going to say, Ariel, your voice got so deep. You boys jumping in. Okay, so linear, quadratic, and cubic. So these visually are what happen at the zeros. So linear might look like this, or it might look like this. We'll get more into that. Quadratic might look like this, or it might look like this. And then cubic might look like this, or this right there. Okay, so these pieces, once we figure all that out, we literally connect the dots to graph. Okay, we're literally going to connect the dots to graph. So I'm going to end this recording here, and then I'm going to start a new recording as we apply all of this to this example, which is like a diet example. It's very, very, very light, very simple, as opposed to the ones that we did, you know, a few weeks back in marking period 1, at the very end of marking period 1, at the beginning of marking period 2, we were doing a lot of graphing of polynomials. So we're, you know, this is going to seem like nothing compared to what we were doing back then. So if you remember all of this, if you think you have it memorized, you like the video, give it a thumbs up for yourself to remember. And if you're like, I need more detail, I need more explained. SOS, you're a crazy person with your stinky Yetis. Put a thumbs down and I will do what I can to help make sure you guys learn all of this, okay?